Hi friends, today we shall be discussing another very simple and popular sorting algorithm called insertion sort. Insertion sort is a very simple and one of the most efficient of the order n square internal sorting algorithms. If the first few objects are already sorted, an unsorted object can be inserted in the sorted set in proper place. This is the basic principle of insertion sort. Insertion sort is an example of an incremental algorithm. It builds the sorted sequence one number at a time. It is an algorithm that many people intuitively use for sorting cards, and it is very easy to illustrate on the deck of cards. To sort the cards in your hand, you extract a card, shift the remaining cards and then insert the extracted card in the proper place. This process is repeated until all the cards are in the correct sequence. This is illustrated in the following slides. Key ideas of insertion sort. First, insertion sort always maintains two zones in the array to be sorted, sorted and unsorted zones. Second, at the beginning the sorted zone consists of one element, the first element of array that we are sorting. Third, on each step the algorithm expands the sorted zone by one element, inserting the first element from the unsorted zone in the proper place in the sorted zone and shifting all larger elements one slot down. The algorithm is: get a list of unsorted numbers, set a marker for the sorted section after the first number in the list, repeat steps 4 through 6 until the unsorted section is empty, select the first unsorted number, swap this number to the left until it arrives in the correct sorted position, that is until the next number to the left is smaller or it has reached the head of the list, advance the marker to the right one position, at the end we stop. As seen below in the slide, the sorted section has 3 elements and unsorted section has rest of the elements. We then see how the first element in the unsorted section 45 is next picked and inserted in its correct position in the sorted section, increasing the size of sorted section by 1. We explain the algorithm with another example. Consider an array of 5 elements with values 98, 23, 45, 6 and 14. In the beginning, the sorted section has only one element 98, while other 4 elements are in the unsorted section. The first element from the unsorted section 23 is picked and compared with 98. As 23 is smaller than 98, so they are swapped. The next element 45 is then picked from the unsorted section and compared with 98 and 23 and inserted after 23. The next element 6 is compared with 98, 45 and 23 and inserted before 23. The last element from the unsorted section 14 is compared with 98, 45, 23 and 6 and inserted between 6 and 23. As can be seen, there have been total 10 comparisons made by the algorithm. Now we look how the algorithm performs if the array is already sorted. Consider an array containing 6 values 0, 1, 2, 3, 4 and 5 in ascending order. In the first pass, 1 will be compared with 0 and 1 is greater than 0, it stops there. So no swap takes place and only one comparison is made. In the second pass, the next element in unsorted section 2 is compared with last element in sorted section 1, and as 2 is greater than 1, so it stops. Again no swap takes place and only one comparison is made. Similarly for 3, 4 and 5, only one comparison is made while shifting them from unsorted section to sorted section. Thus, to sort an already sorted array of 6 elements, only 5 comparisons are made. Implementation. The code in C for insertion sort is as shown on the slide. There are two loops in the function. The outer loop runs size minus 1 times, where size is the number of elements in the array. The inner loop moves elements of sorted section A from 0 to I minus 1 that are greater than key to one position ahead of their current position. This loop will run at most I times, where I is the size of the current sorted section, and if key is greater than A I minus 1, the largest element in the sorted section, the loop will not be executed even once. Performance. Insertion sort is a simple, good, middle of the road choice for sorting lists of a few thousand items or less. Best, worst and average cases. Insertion sort performs best if the element list is already sorted. In this case, as already seen, during each iteration, the first remaining element of the input is only compared with the rightmost element of sorted subsection of the array, and so the number of comparisons are n minus 1 only, giving the running time of order n, which is best for any sorting algorithm. Thus, to sort an almost sorted array where say only a few elements are out of place, insertion sort is most efficient sorting algorithm. The worst case input is an array sorted in reverse order. In the worst case, the list must be fully traversed. We are always inserting the next smallest item into the ascending list, as shown in following slides. Thus, the number of comparisons are 1 plus 2 plus 3 going up to n minus 1, which is order n square. On average, each insertion must traverse half the currently sorted list while making one comparison per step. Thus, the number of comparisons will be roughly equal to 1 plus 2 plus 3 up to n minus 1 divided by 2, which again is order n square. As the average and worst cases are quadratic, this makes insertion sort impractical for sorting large arrays. However, insertion sort is one of the fastest algorithms for sorting small arrays, even faster than quick sort. Advantages of insertion sort: simple to code, very good performance with small lists, very good when the list is almost sorted. In this case, very few comparisons need to be performed. Sort stable, which means it keeps the relative positions of the elements intact. Very memory efficient. It only needs one extra storage location to make room for the moving elements. Good with sequential data that is being read in one at a time, for example tape, hard disk or data being received sequentially. Disadvantage of insertion sort compared to alternatives: very poor performance with large lists, not as quick as merge sort or quick sort. Conclusion: with this we come to the end of today's lecture. Today we had discussed insertion sort, a very simple but efficient algorithm for sorting small number of elements. Though its average and worst case running time is order n square, but it still is in general much faster than selection sort and bubble sort. We conclude our today's lecture by showing an excellent video created by Spencer University, in which insertion sort has been nicely depicted in form of Romanian folk dance. thanking you.